In Lesson 1, we will cover an introduction to the application framework. Specifically, we will discuss what is an application framework, we will discuss what the features and the concept are, and we will actually look into running the system. The NI software-defined radio platform includes both software and hardware. The software is Live Communications, which is a development environment rich with the features that you need to actually implement your prototype. The hardware could be many different options, such as a USRP Rio for standalone prototyping, or a PXI platform with Flex Rios and adapter modules for more measurement-grade RF. The application frameworks can optionally be purchased in addition to Live Communications, and they implement standard protocols such as Wi-Fi or LTE or MIMO. On top of that, we or partners have created application examples such as ones looking at software-defined networks with NS3 or Wi-Fi and LTE coexistence or device-to-device communication, which are available free of charge if the application frameworks are purchased. The purpose of the application frameworks is to provide reference implementations of common wireless standards. The application frameworks provide access to all of the source code, are modular and easily modifiable in design, and are ready to run out of the box with over-the-air signals. They are intended as starting points for the implementation and validation of your new algorithms, systems, and testbeds. As food for thought, some examples of LTE-based prototyping are research on new radio access technologies for 5G, the exploration of new modulation and coding schemes, implementing improvements on the receiver algorithms such as synchronization, channel estimation, or equalization, experimentations with new scheduling and resource allocation schemes, or things like coexistence research or MAC layer functionality. Now let's look at the features and concepts of what are implemented in the application framework, such as which features are available from the LTE standard, how the system is designed, and what are the options within which to operate it. Now let's look at an overview of the key features. As mentioned previously, the application framework provides the capability for over-the-air data transmission, provides a real-time capable physical layer implementation, and enables setups with multiple nodes or single device loopback. Specifically, in the application framework, you will see OFDM modulation and demodulation, channel encoding and decoding for control and data channels, control channel-driven data channel coding, synchronization based on the primary synchronization signal or PSS, cell-specific and UE-specific reference signals, basic MAC functionality to enable packet-based transmission, and feedback channel for rate adaptation. Now let's look at an overview of the whole system. The system comprises of three main components: the host, the FPGA, and the RF. The host primarily provides a graphical user interface for user control and configuration and display of plots and graphs and other data. The host also provides a UDP interface for data streaming from things like a video. The FPGA implements most of the computationally heavy operations, such as decoding in the IFFT, and does things like impairment corrections from the RF. The RF front-end has the digital to analog converters and the analog to digital converters, in addition to doing the up and down conversion from your desired RF frequency. In terms of hardware, the host is usually going to be a PC or a laptop, and the target will either be a USRP Rio and a Flex Rio plus an adapter module. The whole system runs in real time because the signal is generated on the FPGA. In other words, we're not doing playback of pre-recorded signals, but have a fully functioning real-time system. To review abbreviations and terminology that we will see throughout the course, ENB or eNode B is going to be our base station, or evolved node B, which is the term in LTE. UE will be our mobile phone or user equipment. DL will represent downlink, or transmission from the eNode B to the UE. UL will be uplink, or transmission from the UE to the eNode B. TX will be the transmitter, RX will be the receiver. 3GPP is the third generation partnership project, which is the industry consortium that looks at standards such as LTE, and LTE, which stands for Long-Term Evolution, which was originally introduced by the 3GPP in Release 8. The transmitter and receiver are executed on a Kintec 7 FPGA. These are housed inside the USRP Rio or the Flex Rio card, depending on whichever you have. The Kintec 7 FPGA will be connected to our transmitter and our receiver. The LTE application framework specifically implements a subset of the 3GPP LTE Release 10 physical layer. Interoperability between the LTE application framework for TX and RX exists, but it is not possible to actually connect commercial base stations or mobile phones to the application framework without modifications. In the out-of-the-box application framework, there are four main components: the TX and the RX on the eNodeB and the UE. In the application framework, there are two ways to group this functionality. Option 1 is when you have two FPGAs, or software-defined radios, one for the eNodeB and one for the UE, which is a distributed setup. Option 2 involves having just one FPGA in which half the eNodeB and half the UE are implemented on that one FPGA, and in this case only the downlink is implemented and there's no uplink. In the LTE application framework project, these two options are realized with 3 different bit files for the FPGA and 3 different main VIs for the host. In the distributed scenario, where the eNodeB is on one FPGA and the UE is on the other FPGA, the eNodeB has a host VI and an FPGA bit file, while the UE has a host VI and a separate FPGA bit file. In the loopback scenario where there's just downlink from the eNodeB to the UE, all on one FPGA, there's just one host VI that is called downlink and one bit file that is also called downlink. For option 1, where the eNodeB is on one FPGA and the UE is on the other FPGA, you can stream video in the downlink. In this setup, you would have 2 different hosts, either 2 laptops or 2 PCs or some combination, and 2 FPGA targets. For the eNodeB and the UE respectively, the host is going to run that respective main VI, and the FPGA is going to run that specific bit file. In the video streaming, what ends up happening is you have a data source on host 1, which is the eNodeB, which via UDP is communicated to the main eNodeB VI on the host. Then, through a DMA FIFO, the data is piped down to the eNodeB transmitter on the FPGA. This is then transmitted over the air and received by the UE RX. From the FPGA, this goes through DMA FIFO up to the UE main VI, again through UDP, and then to a data sync on the second host of the UE. The signal-to-noise ratio calculation and feedback generation goes like this: from the UE host via DMA FIFO to the UE transmitter, over the air to the eNodeB receiver, via DMA FIFO from the FPGA up to the eNodeB main VI, which then feeds into rate adaptation. Option 2 also allows you to do video streaming, but this time in loopback. In this case, you would have one host, a PC or a laptop, and one FPGA target. Your host would run the downlink VI, and the FPGA would run the downlink bit file. In this case, your data source would communicate via UDP to the downlink main VI, and then go via the DMA FIFO to the eNodeB transmitter, which would be transmitted over the air, received by the UE receiver, piped back up to the host via DMA FIFO, and then to your data sync via UDP. And in this case, uplink happens via loopback. In the application framework, the control channel is going to drive the data channel. The DCI, or downlink control information, and the data source are passed from the host to the FPGA. Both are then going to be encoded, but the data channel encoding is going to be based on the content of the control message. It's also important to remember that the control message is applied for each subframe. Okay, now in section C, we're actually going to look at the system running. In exercise 1, we're going to set up and run the LTE application framework. And then exercise 2, we're actually going to do some experimentation with the host configuration settings of the physical layer. Exercise 1.1. To set up and run the LTE application framework, you need to follow 5 steps. First is to set up the hardware. 2 is to check the hardware manager to make sure everything is properly connected. 3 is to create a new project instance. 4 is to check System Designer and NIMAX. And then 5 is to run the host application. Let's walk through these steps together. This is what the hardware setup would look like in step 1 when the eNode B and the UE are separate nodes. Remember that each node consists of a control PC and a radio. In this case, you're either going to use network splitters and attenuators or antennas to communicate data back and forth between the radios. It is important to note that you must first power on your USRP Rio and then power on the laptop, because the USRP Rios stream data back to the PC via PCIe. As you might expect, this is what the hardware setup looks like with option 2. In this case, the eNode B and the UE are single nodes, where again the node consists of the control PC and a radio. As before, you can either use cables and attenuators or antennas to communicate between the transmitter and the receiver. And as before, make sure you power up your USRP Rio before your laptop, because the USRP Rios are PCIe devices. Moving on to step 2. In Lobby Communications 2.0, there's a tab in the lobby at the top called Hardware. This is a new feature in Lobby Communications 2.0 that allows you to check and see what hardware is connected to and registered by the system. If you properly connected your USRP Rio, you should see your device show up with some form of alias to indicate that it is registered in the system. Now in step 3, let's open up a new instance of the application framework. From the lobby in Lobby Communications, which is what opens when you first open the product, or which can be accessed by the house-looking button in the upper left, go to the Projects tab and then scroll to the bottom. There you should see a folder for application frameworks, assuming you installed the application frameworks. Within that subfolder, open up either LTE Design USRP Rio or LTE Design Flex Rio, depending on which hardware you are going to be working with today. From the project that you just opened, you should be able to check System Designer. You can get to System Designer either by going to the tab at the top, going to View, and then System Designer, or by double-clicking on LTE Design USRP Rio version 2.0.1.lv project from the Files tab on the left side. In this, you should see the graphical representation of your hardware system. If you also go to NIMAX, which is accessible from the Start menu, you should also be able to see the same USRP Rio registered to triple check that your hardware is actually present. Finally, we should be able to actually run our project. If you have option 1, you will need to open up the host VI LTE host eNode B and the host VI LTE host UE from the corresponding laptops. Or if you're doing downlink, you need to open up LTE host downlink. In all of these cases, you want to then check the Rio device, which should match the alias in System Designer and NIMAX. You then want to check the device bandwidth and make sure that the right one is selected for the device that you have. Finally, check the TX and RX frequencies to make sure that the frequency that you transmit at is the frequency that you're going to actually listen at on the other side. And then press Run. What you will then notice in the upper left is the FPGA ready icon will turn blue, which indicates that the FPGA bit file was properly deployed to the FPGA and it is ready to transmit data. Then you toggle the switches at the top to switch on the TX and the RX, and you should see the symbol that you're transmitting, the OFDM symbol, and the symbol that is being received in addition to the constellation and other data like throughput. In exercise 1.2, let's now experiment with some of the host settings to actually see what happens to this real-time system we have. A few examples of what you can do are change the MCS and the PRB allocation in the transmitter. In this case, you should observe changes in the spectral mask. You could also change the RNTI in the transmitter and the receiver, and observe successful decoding only when UEID matches in the TX and the RX. You could also try changing the CCE offset in the transmitter and in the receiver, and notice that the position of the PDCCH in the radio frame needs to match in both the TX and the RX. Also try reducing the transmit power or unscrewing the cables, and observing the changes in the channel estimation and the PSD plots. All of these different options should be things that are on the user interface in your main host VI. In exercise 1.2, let's now experiment with some of the host settings to actually see what happens to this real-time system we have. A few examples of what you can do are change the MCS and the PRB allocation in the transmitter. In this case, you should observe changes in the spectral mask. You could also change the RNTI in the transmitter and the receiver, and observe successful decoding only when UEID matches in the TX and the RX. You could also try changing the CCE offset in the transmitter and in the receiver, and notice that the position of the PDCCH in the radio frame needs to match in both the TX and the RX. Also try reducing the transmit power or unscrewing the cables, and observing the changes in the channel estimation and the PSD plots. All of these different options should be things that are on the user interface in your main host VI, and notice that certain parameters, such as the ones highlighted in yellow at the top, only take effect when you restart the TX and the RX. In other words, when you turn the TX and the RX switches just above them from off back to on, whereas other parameters take effect on the fly, such as the MCS and the PRB. Other parameters only change or take effect after restarting the VI, such as all the hardware and bandwidth configuration stuff.